Lecture 10. Lecture 10. So now we have to start the discussion about diffusion. So in the previous lecture, at the end of our previous lecture, we have thought about this one. If we have just a position where we have more electrons, and if we have less electrons, then what will happen? If we wait for a long time, then yes, there will be net flux from one from the other one, not this way, but only this way. So that is related with a phenomena called as the diffusion, and it is not for charged particles and all other uncharged particles can diffuse. For example, here we have a diffusion of ink, and you can see that starting from this originally highly concentrated location of our ink molecules, after that it is now diffused all over our system. So in this case, of course, the ink molecule can have certain partial polarization. However, it is not fully charged. However, it is diffused. So it's nothing related with its charge state. It's just diffuse over the system. So since it is not for charged particles, so no polarity is expected. This is on the contrast to the phenomena called as drift. In the case of drift, everything was just dictated by the charge, so flux was heavily dependent on the polarity. However, in this time, no polarity is expected. Simply speaking, yes, here we have more electrons and less holes, then the flux will flow in this way. Quite similarly, so if we have more holes and less holes, then still the direction of its diffusion flux will be the same. So although they have different charge states like minus Q and positive Q, but that doesn't matter. So they give the same result. So I have prepared a simple game once again. So maybe you remember that when we consider the drift phenomena, we just introduce a normalized game where every player just gets some velocity 1 after one time step by action of acceleration. And we can do quite a similar thing, normalize the game once again. Here, as an initial condition, I have prepared many particles. So here we have number 0, starting from 0, 200, 1000, and each position corresponding to, for example, 600, we have 100 particles. So maybe you can easily understand that I have prepared here in this box 10 kilo particles have been prepared in this case. And in this case, the number is somewhat lower. I don't remember exactly, maybe 20. So that is corresponding, I don't remember exactly, but maybe that is about 20,000 particles. Then what happens? At the initial condition, I have prepared more particles and less particles. After that, just individually ask to these guys, please move either one position to the right or one position to the left. So there is nothing, just staying, either going to the left or going to the right. So that is the situation I have assumed. So after 10k turns, so it means that if one is quite lucky, what it happen? So let's assume that. Oh, here is my okay. So let's consider a particle originally or initially located here. If it is quite lucky, then what will happen after 10 or 1000 tons? If it is always going forward, or to the right, then eventually it will arrive here. Or if it is quite lucky, then maybe it can reach at this position. But please think about the probability for one particle to be lucky enough to reach the end of its system. How lucky is it? Or how probable is it? So maybe you understand that is extremely low probability, because every time the probability is just half to go to the forward or go to the reverse or backward. So we have to consider this kind of probability. So that is extremely low, so maybe it is not very much probable. So more probable way is, yes, sometimes it is lucky, so it goes, for example, 3 or 4 steps. After that, it just goes back and go to that way, also go to the backward. So that is just randomly placed so many times. So eventually its movement will not be that much moved from its initial position. So if I ask one particle, so let's make some prediction. After 1000 tons, then whether it will be on the right side of its initial position or on the left side of its initial position, what will be the probability? Since we have no preference about going forward or going backward, so you know that at least expectation value will be exactly here. So we can go, for example, 500 times go to the forward and 500 times go to the backward. So eventually when we make just average, so average position will be the same for each particle. Everything is just so we have to wait a little bit because the pencil is stuck. Okay, so for each particle, this situation is quite understandable, and for every particle, it is just coining +1 or -1. However, so please have a look at this progress of the system. What happened for each one? Is its initial position just stays, or its probability is just to go to that way or that way, but after certain tons, for example 10,000 tons have passed, then how about your feeling about the shape? So initially there was a abrupt difference between more particles and less particles, but now after some time later, now you can see that this is the case we can have. So what happens? So simply speaking, here we had certain particles but that is just moved into this relatively lowly populated place. So that is the case, and this is nothing related with polarity, whether that is having positive sign or negative sign, that doesn't matter. It just shows the random motion of each particle. For each particle, it has no clear view for its movement. It is just going forward or going backward. However, it's a collective motion. Their collective motion shows certain behavior, like movement, net movement from more populated place to the less populated state. This is the form of diffusion. Okay, so if we consider, for example, if we consider in addition to this diffusion, if we consider also drift, then what will happen? For example, let's say that instead of this one, we just add in that way. If one is moving forward, then we just add 1.5. And if it is selected to be going minus, then it is just going minus 0.5. Why we have this kind of number? Because due to the diffusion, it is going back. However, since we are assuming certain drift, so the pushing force, our particles all toward forward direction. So in this case, then net movement will be just not just having this kind of smoothing, but also net movement of this position into that way, that way, that way. So you can now understand inside our system we have two different transport mechanism. So once again, in the case of drift, all of our particles are accelerated at the same direction. However, in the case of diffusion, there is no clear preference for certain direction, but collective motion just gives us an overall movement. So now, let me just make some equations for this phenomenon. So we can consider flux. Flux means that, so number of particles crossing certain cross sections per unit time. So for example, we can think that certain direction, a certain area, surface, and just counting the number of particles flowing through this area. Then that is corresponding to the flux of our particle. Of course, we can consider, for example, this flux is not only for electronics. You can consider, for example, flux of airplanes. For example, let's think about this one. Here, we are now living in Gwangju city, and here we are here. Oh, this is Gist. And nearby we have a certain airport, and every day there are some airplanes trying to landing in that way. So in this case, we can, instead of the flux of electrons or flux of holes, we can also consider certain flux of airplane. For example, for during 1 hour, how many airplanes are coming to the Gwangju airport? That can be measured and be quantized or quantified. And you know that if we try to measure this quantity, then there will be a certain position in the sky where its flux is quite high, because you know all of our planes are controlled by control tower, so they are asking to fly only the given route, so already allowed it by the control tower. For example, let's think about the flux of an airplane in this point or that point. Can you measure the number of airplanes flying just on top of my head? So of course we can try to define it, but its value will be clearly 0. Also, if we go to the very high position here, then of course the number will be quite small. What I wanted to say is flux is more general concept beyond the electronics. We can always think about the number of countable particle, countable physical thing per unit area and unit time. So now we can consider flux. However, flux of what? Flux of electrons or flux of holes. In this case, from the flux for our electrons or holes can be considered in this way. Although I have written here only for electrons, but we can also say that flux for our holes can be written in the same form. Here I wanted to say, here we have the same sign, minus sign and minus sign, which it does not depend on what? Depend on the charge state of our particle, because you know this diffusion phenomena is nothing related to the charge state. So we have a same sign and just to depend on gradient of the density. Simply speaking, particles are moving from highly populated, densely populated position to the lowly populated position. That is the one we can think here. Okay. So, however, there is something makes the students confused. So, in terms of flux, both of electrons and holes, they share the same form because it is not related with the charge state. However, more frequently used physical quantity is current density. Current density is simply given by, for example, in the case of electron, just electron flux multiplied by the charge carried by our electrons. Each electron carries minus q, so that's the reason why when we express the electron current density, we have to multiply minus q. Now think about the hole. Each hole carries positive q, so our hole current density should be written in this way, not multiplying minus q. So although diffusion mechanism itself is independent on the polarity, since our quantity of interest is more frequently current density, so it seems that our diffusion current densities, so they have certain dependencies on the polarity. However, please note that when we just count the movement of electrons and holes only, then they are really independent on the polarity. So now you can understand this is the case for electron and hole. So please try to remember your equation for drift. Do you remember? So in this case, Q mu n and electric field, and JP drift case it was also given by QPPE. So maybe you feel that, oh, how can he memorize all kinds of different things? But at least during this semester, you also should remember these relations with correct sign. Sign is important because, if I introduce something wrong, for example, minus sign, that means that you just convert the sign of your or movement of your holes. Then that will destroy the physics. Okay. So yes. Then let's go to the next part. Oh, here we have an example, so I will just skip the example. So please just have a look at our lecture material. So when we have a certain density and another density separated by certain length scale, then you can easily calculate the number. So today's main topic is all related with current density. There are so many different ways, various ways to express current density, and sometimes that makes some confusion to our students. So today we wanted to introduce many different forms and make a clear distinction between different notations or different expressions. So first of all, let's start the concept of total current density. What is the meaning of total? In this case, we are now assuming this kind of things. Since we are working in the semiconductor, we have electrons as a moving particles. Also holes, they are moving. However, we do not think that donors are moving. Donors are called as immobile. They do not move. Also, how about acceptors? Also, we assume that they do not move. Then is it true that they do not move or not? Even the atoms or atomic cores, they can move inside our semiconductor in a long term. How long is it? Orders of years, 10 years. Once you fabricated your new chip, then one atom can be placed some places. After running that device for 10 years, can you confirm that same atom is located at the same position? Actually not. They are actually moving. However, you know that time scale, days, months, years, is much longer than our interested time scale. What is our interested time scale? Our interested time scale is nanosecond, or for example microsecond, millisecond, or something like that. So therefore we can assume that they are immobile. Okay, and in this case, then now total current density, overall current density, can be obtained from only moving particles. So that's the reason why we consider electron current density and hole current density. So think about this one. If your system have other moving particles carrying charges, then you have to also consider the current density originated from that moving particle. However, inside our system, semiconductor devices, typically we assume that only electrons and holes are moving. Yes, that's the reason why we have particle current densities originated from these two species. And other one is related with displacement current density. Displacement current density is having the form of this one. So here we introduce epsilon times electric field. So you know this quantity. This is electric field, and this is the strength of the force exerted to your charged particle. So that is electric field, and here you have some quantity typically called as written with epsilon. So this is permittivity. So this is permittivity, and it has a certain number, and when we multiply these two quantities, we can obtain the quantity called as displacement. And simply speaking, the displacement current density is the time derivative of displacement vector. So therefore, if we consider a steady state condition, simply speaking, if we consider DC case, then everything related with time derivatives goes to 0. So in that special case, we can completely neglect the contribution from displacement current density. However, in general case, of course, we have to consider this one too. Okay, please understand this one. For example, in the case of small signal or time varying phenomena, the displacement current is essentially important. But for a while, in this lecture, we just concentrate on electron and hole current density. So now let's come back to the electron current density. You can easily understand the current density has two terms, the first term and the second term, and they are identified as one is due to drift and one is due to diffusion. Also here we have drift and diffusion. So simply speaking, the net movement of our particles like electrons and holes are determined by the sum of two actions. One is drift and one is diffusion, because this particle is charged and we can assume the density difference at each position. Okay. Yes, this is the general form we will use. And here we introduce one important relation called as Einstein relation. So, but we must understand this restriction at equilibrium. At equilibrium means that when do you have equilibrium? Now think about this one. You have a certain wafer or chip, and on top of its surface, now you have two metal pads. So this is metal pad, and this is another metal pad, and you apply certain voltage, because since this is just metal, wood metal, you can make also another metal wire, and this metal wire is connected to a certain DC voltage source. Also, you can do the same thing for this way. Yes, and there is another voltage source. You can freely control the value of this voltage source and that voltage source. When, for example, let's just say this is V1 and V2, and when V1 equal to V2, then is it in the equilibrium case or not? Yes, in this case, if we don't apply any other excitation to this system, only voltage is the only excitation, then we can say that this system is at equilibrium. However, if V1 is not equal to V2, in this case we can say the system is in the non-equilibrium case. Why? It is because, here we have voltage source and voltage source. Two voltage sources are now trying to I will explain later, but trying to in some rough way try to govern the device. So I think that this is not very scientific. What is the meaning of govern here? But I will explain it later today. Simply speaking, if we have two different voltage sources connected to the system, then they have a tendency to make some influence on the device. And when they have the same voltage, it means that happen to be they are in agreement. So they wanted to make the same situation. So in this case, we can say the system in the equilibrium. However, unfortunately, if we have the condition where V1 and V2 are different, then both of our V1 and V2 are trying to do something, but the final goal of these two voltage sources are not identical. So they are conflicting inside our device. So that is the essential part of the non-equilibrium. So simply speaking, you have to understand, why do we have non-equilibrium? Which one generate non-equilibrium when we have voltage sources? So we must understand voltage sources are trying to do something to our small device, and when they are not in the agreement, that is the action of our semiconductor device. So simply speaking, in many cases we are with non-equilibrium case. For example, simply speaking, you apply just 1 volt difference to your metal pad, then is this the equilibrium or non-equilibrium? Certainly this is non-equilibrium. However, I wanted to say that Einstein relation is strictly valid only in a strict sense, only valid at equilibrium. However, at equilibrium we can certainly say that this is the true, this is a law. Yes, this d sub n and mu sub n, mobility, and d sub p and mu sub p, they have the clear relationship, proportionality between these two quantities. Okay. So sometimes this dn, depending on the literature, d sub n, this is electron diffusion coefficient, but sometimes it is called as electron diffusion constant or electron diffusivity. They have many similar names, but they are used interchangeably. So please, sometimes I will say that diffusion constant or diffusion coefficient from the same person, so don't be confused. They have different names. Anyway, here we have the proportionality between this mu n and dn and mu p and dp, and their proportional coefficient here is simply what? kbt divided by q. What is it? This is just your thermal voltage, and you have to remember the value at 300 Kelvin. No, this is about 25.85 millivolt at 300 Kelvin. So now this is taken from Professor Park's book, and you can see that as a function of doping concentration, the left y-axis shows mobility, and right y-axis shows diffusion coefficient. So, for example, for same value, it is corresponding to 1000 from for mobility, and for other one here, this is corresponding about 25. So why do we have this relation? Because we have Einstein relation. So simply speaking, if you know the electron mobility at equilibrium, you automatically understand the value of diffusion coefficient. Also, when you know mobility, whole mobility, now you know the diffusion coefficient for holes. So that's the reason why, instead of separately modeling this mu sub n and d sub n, sometimes people just try to model only mobility, and by assuming this Einstein relation to every case, then they just generate this d sub n. At this moment, you must have the same question to me: why it is allowed? So you stress that this is valid only at equilibrium, but in order to model this diffusion coefficient, we always just rely on this Einstein relation. So I mean that we are doing beyond the validity of this relation. Einstein relation is valid at equilibrium only, but we are now applying to this relation to everywhere, every case. So what happened? Actually, this is not allowed. We are doing beyond the thing, and we are not very much accurate in this sense, but since it is too convenient, so we are doing that job in our usual modeling. So please understand, we are not very accurate in this sense. So anyway, if we just apply the Einstein relation to our previous current density equation separated by drift term and diffusion term, they can be merged. Wow, how can we merge them? So when you have a look at this drift term and diffusion term, of course you can find Q is shared, but this is just a constant. But when you have a look at your mobility and diffusion coefficient following the Einstein relation, you can now, this dN can be written as thermal voltage multiplied by mobility. Wow, so we can have a common factor like Q times mu n. Then let me just write down the merged form. So we also pull out this electron density. Then please try to write down the remaining term, or the drift term and diffusion term by yourself. You can do it. So if we take just Q, mu, and N, then remaining one is just electric field here. For drift term, that's it. And in the case of our diffusion term, what happens? Here we have kBT over Q. Why do we have this term? It is originated from the Einstein relation, and the remaining one is 1 over n and gradient of n. So maybe you may ask me, why do we have this 1 over n? But since we have pulled out our n, therefore we must have 1 over n. They are cancelled out, and here we have this form. So now let's go to, if we do this job, then that will be the form for our electron current density, and this is form for our whole current density. Maybe you feel I'm just playing with the equations without any physical interpretation. Right now it's okay, because this and that, here we have some factors. So simply speaking, try to read this equation. Electron current density is given by what? This product. And what is this product? Q times mu n, and you know it. This is the conductivity of your electron gas. And here you have something. What is it? This is also conductivity of your whole gas. In your system, in your material, you have electron gas and whole gas, and each of them has conductivity. And we are just measuring the conductivity. After that, we have certain thing which is quite resemble to the electric field. So please concentrate on this part. Here we have gradient of electrostatic potential. What is it? Gradient of electrostatic potential is proportional to the electric field. But in this part, we have additional form. This is corresponding to the electric field. Actually, it's minus value. And here we have some correction. But overall, what we can say is, simply speaking, Jn is given by conductivity multiplied by certain thing. Here, certain thing quite resembling the electric field. That's it. So maybe you feel this way. Generally, Ohm's law in a microscopic way is taught as in this way. J is given by sigma, usually used for conductivity. After that, electric field. You know this is Ohm's law. The current, more precisely, current density is proportional to the conductivity and also magnitude of applied electric field. Now you understand, for electron current density, we have a slightly generalized form. Conductivity of our electron gas multiplied by certain quantity quite similar to the electric field, and that correction is shown here. Then how can we express this term into our terminology? What will be the case? Simply speaking, If we consider electric field, then we can define it in that way. Gradient of electrostatic potential was electric field, but now we have a certain vector which is quite close to the electric field but not exactly the electric field. Then how can you do that? Quite similarly, we wanted to do this job. Introduce a scalar field, and by taking the gradient of this scalar field, we wanted to generate a vector which drives the electron current. Also for holes, we wanted to introduce a scalar quantity whose gradient generate the driving force for our whole case. So that's the reason why we have to concentrate on these terms inside this square bracket. So let's try to do something. It is quite straightforward. So now let's try to revisit our expression for carrier concentration. It is nothing but I just show it to you in that way. So electron density is given by just exponential of a certain quantity. But certain quantity means that the difference between our intrinsic carrier density, intrinsic Fermi level and Fermi level. So it was already explained, but now let's go to the next step. Here we just change the notation, nothing new, and don't be fooled by this just change of notations. Whether I'm using this kind of potential like quantity or sometimes using the energy like quantity. So this E sub I or E sub F, they are energies. And here we have electrostatic potential and Fermi potential. Both of them are in the unit of voltage. But that doesn't make any difference because all quantities appearing here has some relation like this. This here, voltage like quantities multiplied by minus Q generate energy like quantities. Simply speaking, I'm saying that E sub I can be expressed as minus Q times electrostatic potential, and here we have a Fermi level, and in order to pointing out the Fermi level, we just introduce minus Q times and Fermi potential. Then what happens? Both of them having just minus Q in front of it. So this one is minus Q, and this one is also minus Q. They are all pulled out, and we can make this quantity. What is it? Once again, summer voltage. And here we have expressions like this. So I want to say this is quite simple and straightforward, but let me just emphasize once again. One expression for electron density is expressed as intrinsic carrier density times exponential of electrostatic potential minus Fermi potential normalized by summer voltage. So okay, so I will just use the notation KBT over Q because our textbook does not explicitly define a symbol for summer voltage. So we'll try to always use this value for our summer voltage. If I'm working in different semester or different course, then I would say like this one, because this is a summer voltage. But unfortunately, in this course, we have quite a similar notation. That is yes, that is a thresh. This is thank you. So this is reserved for threshold voltage. So usually my preference is use this one for summer voltage and use this one for threshold voltage. But unfortunately, both of them also start from TH. So it's not that easy to say. So following the Professor Tower's notation, I will not explicitly use certain notation or certain symbol for summer voltage. So please understand this one. But anyway, let's just come back. This is an important relation. Electron density is proportional to exponential of your electrostatic potential. Yes, and its value is modulated by the position of your Fermi level. So yes, we know it, but point is, please understand this relation and this relation. If I ask you the validity of these relations, when do you have these relations? At equilibrium. Yes, you have this equation. Even when you have non-homogeneity, I mean that even inside your p-n junction, you have this relation as much as your system is at equilibrium. But if your system is at non-equilibrium case, then some problem occur. Why? Because now nobody can define this Fermi potential. Fermi potential is nothing but this is just another name of Fermi level. And can you define Fermi level at non-equilibrium case? This is not the case, because Fermi level is the property of equilibrium system. So since your device is non-equilibrium system, then it's not possible. For example, our national ID system is the property of Korean people. Let's say that I'm now neutralized to other country, so abandon my nationality and go to the other country. Then now if somebody asks me what is your Korean national ID, then is it valid question or not? So quite similarly, if your system is at equilibrium, then you can ask where do you have your Fermi level. However, if your system is out of equilibrium, non-equilibrium, then it is not a valid question to the position of Fermi level. So concept of Fermi level itself is challenged by this non-equilibrium case. So what we do is, but still we wanted to use this quite a beautiful expression. So let me just try to extend this equation to non-equilibrium cases. So what they do, this is important, what they do is, at equilibrium, electron density can be expressed as phi minus phi f and divided by kBT over Q. That is a rule, and once you know phi and well defined Fermi potential, then now you can consider the electron density. However, at non-equilibrium case, please note this difference here and that. Although looks quite similar, but instead of defining this well-defined Fermi potential, we introduce some strange quantity called as electron quasi-Fermi potential. We define this strange quantity. Then, is it allowed? Please understand the introduction of this quasi-Fermi potential is nothing related with very accurate argument. We just introduce this quantity to describe what? To describe electron density. Now we assume that, oh, there exists the well-known number of electrons. This is known, and we know electrostatic potential. This is also known. Then how can we describe our relation between electron density and electrostatic potential? Just adjust our relation, we introduce a certain number. There is not much physical meaning. So then, of course, at equilibrium case, we can always define certain well-defined Fermi potential. However, in the case of a non-equilibrium case, since the electron quasi-Fermi potential or electron or whole quasi-Fermi potential, they are introduced just to describe electron density and hole density, so we need more relations. So please understand, they are just phenomenological description for our electron density. This is not a rigorous law, but fortunately, when you introduce this electron quasi-Fermi potential and whole quasi-Fermi potential, life becomes extremely easy. So let's have a look at it. So starting from this relation, let me just I will just show you the manipulation. N over Ni will be exponential of something. Something means that this one is something, and take the logarithmic. Then you will have log of N over Ni equal to kBt over Q phi minus phi n. So are you with me? Then just to move this summer voltage to this part, kBt over Q. Then you will have this expression. So finally, you can understand from this one, your electron quasi-Fermi potential is simply given by electrostatic potential minus correction term. What is the correction term? The correction term is given by summer voltage multiplied by normalized electron density. Okay, so please remember that our main motivation is to express our electron current density as a product between electron conductivity and other electric field like quantity. So now we are coming back to this case, and we know that the electron quasi-Fermi potential is a electrostatic potential like quantity with certain correction. Then let me just take the gradient. Then what happens? Gradient of your electron quasi-Fermi potential will be given by simply gradient of what? Gradient of your electrostatic potential. And after that, you have gradient of this quantity. Well, log n I. But you know once again, when you calculate this quantity, log of n over ni, you know log of n over ni can be calculated in this way: log n minus log ni, and log ni is intrinsic carrier density, and that is uniform. So when we take the gradient, it vanishes. So the remaining thing is just gradient of log n. And everybody know that log something and its derivative is given by n and gradient of n. If you don't understand, then please let me know. So simply speaking, it is nothing but d over dx log x, that is given by 1 over x. Or if you have f of x, then it is given by f over x and f its first derivative. So you know this relation. So now let's come back. Although we have gradient of log n, but it can be, without any approximation, it can be expressed as this form. That's the point. Here we have introduced a quantity called electron quasi-Fermi potential. It was just introduced to electron density. However, now after some manipulation, we understand the gradient of electron quasi-Fermi potential is related with electric field and density, electron density change. So please remember this form. And now I wanted to coming back to our current density expression. When we come back to the current density expression, then please have a look at this green underscore part here. So gradient of electrostatic potential modified or augmented by this gradient of n divided by n. So you can easily understand when you come back once again, this is exactly the form of your gradient of quasi-Fermi potential. So now in this case, current density can be, electron current density can be expressed by this form, our electron conductivity multiplied by this quantity, gradient of electron quasi-Fermi potential. Same relation holds for our whole gases. Whole current density can be expressed as whole conductivity multiplied by gradient of whole quasi-Fermi potential. So let me just summarize today's talk. If we consider both of drift mechanism and diffusion mechanism, actually particle current density, like electron current density or hole current density, they have two contributions, drift term and diffusion term, and each of them has their own driving force. In the case of our drift, then gradient of electrostatic potential was the driving force, and in the case of our diffusion, actually gradient of electron density was the driving force. So we have two terms and they are not very good to be manipulated. However, by assuming the Einstein relation and also introducing so-called quasi-Fermi potentials, then after manipulation we can arrive a certain expression like Ohm's law like expression. Electron current density can be expressed as this form, and yes, here we have quite reasonable quantities like electron contribution to the conductivity, and here the driving force originated from the electron quasi-Fermi potential. So let me just state the verbatim taken from the Tower's book. Let me just read this line. The gradient of electron quasi-Fermi potential, this is nothing but gradient of electron quasi-Fermi potential, drives the electron current. Yes, drive the electron current. Same happens. The gradient of a whole quasi-Fermi potential, this is nothing but, yes, this quantity. This one becomes the driving force for whole current. So simply speaking, if you have a certain condition like your electros, your, for example, if when you take the gradient of electron quasi-Fermi potential and let's say that it vanishes, then it means that simply this system is at equilibrium or no electron current at that point. Also, when you have this condition, then there is no whole current, because Jn is just proportional to gradient of whole quasi-Fermi potential. So simply speaking, the gradient of quasi-Fermi potential is an indicator for whether that there exists a certain current flow or not. So please understand this relation. This relation is really important, especially important when you understand the behavior of your p-n junction. Well, I have studied p-n junction already several times, but you know that once you understand the concept of this electron or whole quasi-Fermi potential, then you can understand the behavior of your p-n junction more deeply. So we will visit this concept once again. And now we have only 10 minutes left, and now let's go to our Poisson equation. Wow. Poisson, here Poisson means that the name of a certain mathematician, French mathematician. So this is a Poisson equation. Actually, in a mathematical sense, when we say Poisson equation, that is given as this form. Here we have a certain function which depends on the real space position, yes, and takes the second derivative. This one is usually called as Laplacian. So in a Cartesian coordinate, this is corresponding to second derivative with respect to x direction and y direction and z direction. So anyway, this is a second order derivative. And when it is balanced by certain non-zero, generally non-zero function S of R, then this relation or this equation is called as Poisson equation. Poisson equation is actually nothing related with electrostatics or electronics. This is just a mathematical name for certain categories of equations. And of course, we have a more well-known equation. For example, when we have a special case where this S function vanishes everywhere, then we can assume this form. Then it has its own name. What is it? Its name is now Laplace equation. So Poisson equation or Laplace equation, they are named for some equations having certain form, but when we say Poisson equation, we are using that name for our point of view. So in our context, this is Poisson equation. I think that is better to say Gauss law. We are now considering Gauss law in our system. Simply speaking, Gauss law is the electrostatic rule, and since our electrons and holes and donors, ionized donors and ionized acceptors, they are charged particles. That's the reason why we must solve this Gauss law. And Gauss law is in our field called as Poisson equation. That sounds quite natural because we are considering charged particle, and charged particle will generate electric field because charge is the source of electric field. So that relation from charge to electron density, from so-called law, net charge density, to electric field E, that is described by so-called Poisson equation. Okay, so since we have spent quite a long time about current density expression, but I feel quite happy about introducing this relation, because usually in my former lectures we are in hurry, so usually that part was just skipped. But I think that is quite important. That is, I think that the criterion makes some difference between basic level semiconductor physics course and advanced level. So please try to understand today's lecture content, and we will meet once again in next Monday. Thank you.